Good afternoon, viewers, and welcome to the EduSat live lecture for the science stream. Today we have with us Ms. Vipsa Bhatia from the Department of Electronics and Communication Engineering, Indira Gandhi Technical University for Women. And she has 17 years of teaching experience and several publications in national and international journals, and she has been discussing with us communication and electronic and digital media. So over to Ms. Vipsa Bhatia.
Thank you, Unnati. My topic for today is computer organization and architecture. Most of us are avid computer users. Many of you might be accessing the lectures directly using a computer. Though we know the basic functionality of a computer, how it functions, how it is used, how it is accessed, the interim information about the computer, the internals of the computer still remain a mystery for many of us. And hence the reason for today's lecture, which is computer organization and architecture. Now basically, to explain it in layman's term, an architecture is something that is visible to a person. Talking about the architecture of a building, we are able to see that the building has, there is a ceiling, there are walls, then there are different artifacts to the building. And organization refers to the brick and mortar that is used to build around this computer architecture, Now coming to computer architecture, it refers to those attributes of the system which are visible to the programmer, while computer organization refers to the operational units that are interconnections that are used to realize these architectural specifications. That means to bring about to the user or to the programmer the kind of basic system fundamentals, we need this basic system organization for that. So as an example, to differentiate between computer architecture and computer organization, we say that a computer should have a multiplication function. Now, this is the system architecture which requires the computer to have a multiplication function. Now, to actually implement the multiplication function, we move on to the computer organization, wherein we decide whether the computer is going to have actually a multiplication unit or is it going to have an addition unit, and using the multiple additions we are going to come up with the multiplication. So the two aspects, the architecture being the function to be implemented, and organization means how the function has to be implemented. Now basic functional unit of a computer is made up of electronics. There are circuits and there are signals that are flowing. These are the electrical signals which help the computer to function. Now generally the signals are broadly classified as analog signals and digital signals. Analog signal is a continuous signal which is continuously varying over a period of time. These signals are generally have a lower and an upper limit, and between this lower and the upper limit, the signal may attain any value, and it is very difficult to predict the value that the signal is going to take. The digital signal, on the other hand, is also referred to as a discrete signal. This signal has fixed definitive values that it will take. So we already know which of the values in the set it is going to take. The exact value may not be known, but we know that out of these values, one discrete value is what this digital signal is going to acquire. Now digital signals are usually represented as a high and a low signal. Usually the low is represented by a logic level 0, while a high is represented by a logic level 1. So all the functionality of the computer can be captured through this 1 and 0, and this whole implementation of the 0-1 logic is what is done by using the Boolean algebra. Boolean algebra is basically a set of theorems, the set of rules through which the manipulations on the digital data is carried out. And the number system which is mathematically used for manipulation of the digital data is the binary number system, where binary stands for 2. Since there are 2 digits, 0 and 1, so this number system is called as the binary number system. Now the smallest unit of information in a binary number system is a bit. A single bit is either a 0 or a 1. Now various bit combinations can lead to higher level of data being manipulated. For example, 4 bits together form a nibble, while the 8 bits together form a byte. We have usually come across these terms as bit and byte while working or while discussing regarding the computers. So we know that there is an 8-bit or a 16-bit or a 32-bit system. So this refers to basically the length of the data that can be handled by this computer, its computing functionality. Now, last 50 years have seen the computer technology making incredible improvement. So, earlier computers had no stored program facility. That is, the program that was run on the computer could not store any data. You could just get the result and that was it. The computational power hence was very, very less. The data, there was a lot of repetition because of the no storage, and top of it, the size of the computer was a very huge. The earliest known computer was supposed to house in a complete building. So, that was how big the computer was, and the kind of heat it generated, the kind of power it used up was very, very huge. Enormous amount of power was also utilized. Now, today the personal computer has become very, very small. We are moving towards miniaturization. Right from the computer being housed into that building, we have to moved over to a personal computer, to a laptop, and now even a palm top. So, the technology has made the size of the computer very, very small, and parallelly the cost has also come down. The computers have become much more affordable, much more cheaper as compared to they were there say 20 years back from now. So, this rapid rate of improvement in the computer technology comes from the two facts: advances in the technology that are coming rapidly, and from the innovation that is taking place in the computing design. With the way the technology is growing, the number of innovations that are coming up, newer and newer versions of the computers are coming into the market, and no sooner has a computer system come in, after a while the system becomes obsolete with the kind of progress that we are seeing in computer technology these days. Now, computer design involves various steps. Whenever designing a computer, there are certain attributes which are important to a new machine, which are specified as to what the machine should have, and at the same time, it should not increase the cost of the machine so that it becomes unaffordable. So, the purpose is to have maximum attributes, maximum features, maximum flexibility in the system while staying within the cost constraints. So, these aspects include the instruction set. The instruction set refers to the instructions in the language which is computer understandable. So, as vast an instruction set it will be, the better it will be to have the computer performing more number of functions. Similarly, the functional organization plays a very important role. The logic design, and finally the implementation of the logic design is also an important attribute whenever we are talking about computer designing. Now, computer architecture once again refers to those parameters of a computer system that are visible to a programmer, or those parameters that have a direct impact on the logical execution of a program. For example, the instruction set, the number of bits to be used, the different data types, the input-output mechanism, and the techniques of addressing the memory of the computer all form the part of the computer architecture. Now, computer organization broadly, on the other hand, refers to the operational units and their interconnections that realize the architectural specifications. For example, we say the hardware details which are transparent to the programmer, such as the control signal, the interfaces between the computer and the peripherals, and the memory technology used. The user is not aware of this. User is just using their functionality which is extended to the user via the computer architecture. The organization, on the other hand, remains hidden. However, organization plays a very, very vital role in making this computer usable, making this computer more flexible and more readily available features to the user or the programmer. Now, coming over to a basic computer model, from what we use, what we are using as a computer is essentially a black box, wherein we have some input devices, we have an output devices, there is a memory to store data, and whatever is happening in between is something which is not really clear to the user when we have a look at the basic computer. So, the basic units are the central processing unit, the input unit, the output unit, and the memory unit. The input devices and the output devices are also commonly referred to as I/O devices, means input-output devices, and are also called as the peripherals. That means the devices which are attached to the periphery of the central processing unit. We can view this diagram as the CPU being the heart of the system and input-output devices being the limbs, while the memory stands for the basic storage or the brain or the department where the data is stored. As I mentioned earlier, the earlier computers were not capable of storing data, whereas the computers now that we have a storage facility which is being increased as the technology is moving ahead in time. Now, central processing unit, as I mentioned, is the heart of the computer system. Central processing unit in itself has two different blocks which it is composed of. There is a control unit which carries out the control functions in the sense that it picks up the data from the input unit, transfers the data and based upon the kind of operation that users has desired, and then later the output data after the required functionality is outputted via an output device. So this is all complete carried out under the instructions of the control unit. The second unit is the execution unit, which is actually performing the manipulation of data based upon the required functioning. Once the control unit has fetched the data or made the data available to the execution unit, it directs the execution unit to perform the desired operation. Once that operation has been performed, then this is again given over to the control unit to transmit it at the output or maybe stored it in the memory as required by the user. So execution unit is also called as the data processing unit because that is the one which is actually working on the data and which is actually producing the desirable result. And it internally, the execution unit has registers for storing data. It has an arithmetic and logic unit. Arithmetic and logic unit is basically the unit that is carrying out all the arithmetic operations. By arithmetic operations, we mean the addition, the subtraction, the multiplication and the division operations, and the size of the ALU is determined by the size of the data the computer is able to handle. For example, an 8-bit computer processor will be having an ALU which is able to work on an 8-bit data. Similarly, for a 16-bit data, it will be a 16-bit ALU and so on. And it performs the logical operations also. By logical operations, we mean AND operation, OR operation, XOR operation, NOT operation and so on. In addition, the CPU may also have certain additional registers for temporary storage of data. For example, if I am performing the addition of 3 numbers, then the intermediate sum after adding the 2 numbers is stored in this temporary register. Then it is added to the final number before the result is output to the output device. So it is necessary to have a temporary memory, though this memory will not be very large, but it is always there in the execution unit. So on the whole, we can say a CPU has control function. It has the execution function, that is the bit manipulation function, which it carries out with the help of the arithmetic and logical unit. Now moving over to the input unit, as the name suggests, the input unit is used to input the data or the instructions from outside to the CPU. So the program or the data is read into the main storage from the input devices or the secondary storage under the control of the CPU input instruction. The examples of the input units are the keyboard, the mouse, the hard disk, the floppy disk, the CD-ROM and so on. So these are essentially the peripherals that we commonly use when working upon our computer system. Now the output unit on the other hand is that part of the peripheral which is used by the computer to display the result to the outside world. This can be a display device, this can be a storage device. So there are different types of output devices, the common examples being a printer. Your monitor is a display device and it is again an output device. Then there can be a hard disk or a floppy disk. So these types of disks are also output disks because they are able to store the data for the future use, while whenever we require the data which was obtained from a previous operation, that can be easily seen by reinserting these floppy disks, which are quite outdated nowadays, having the flash drives coming into picture, the pen drives and the CDs that are there. So the floppy is hardly used, but then this was a very important kind of a device which was being used 15 years from now. Now next block to the basic computer architecture is the memory unit, and in my opinion this block is a very vital block because this is where the entire functionality, the data is stored. So this makes it the data available for us at a later date in time, makes the data available for us for manipulation further, makes it available for us for reference in the next overcoming programs. So the unit, this memory unit essentially stores the data. So the main unit is termed as the primary memory, which is the part of the computer system, or it is also referred to as the main memory. Now generally there are two types of memories. There is a volatile memory and a non-volatile memory. A volatile memory is essentially a temporary memory which is available only till the power in the system is on. As soon as the system is turned off or the power is shut down, the data contained in the volatile memory is erased. The RAM of the system is the example of the volatile memory. RAM stands for random access memory. Now, non-volatile memory on the other hand is the memory which is available even after the power is switched on. So, this is a permanent kind of a memory, and the example for this kind of a memory is read-only memory, which is ROM. And there are other modifications of the ROM, which is a programmable ROM called PROM, electrically erasable ROM called EEROM, and EPROM, which is erasable programmable read-only memory. We will be discussing about these in detail as we move forward in the lecture. Now, as I mentioned, the main memory is the primary memory, which is an integral part of your computer system. Besides that, there is a secondary memory. This is the memory which is non-volatile memory and can be used for permanent storage of data, and this is additionally applied over and above your main memory. The example for the secondary memories include the pen drive, the magnetic tape, the CD-ROM, the external hard drive, etc. So, these kinds of drives are additionally available to the user to take the data, to store the data, and then use this data later. These can be detached from the system, and whenever required can be reattached to the system through different ports, such as the USB port, which is commonly used, and the data can be accessed at a future use. Now, let's come to the working of a computer. How does a computer work? Now, as I mentioned earlier, the arithmetic and the logical unit is an integral part of the CPU. All the computational operations are performed by the ALU. And as I mentioned before, the operations such as addition, subtraction, multiplication and division are all performed by the ALU. Now, control unit directs the ALU as to when it has to perform a certain operation on a certain data. Only under the instruction of the control unit is the ALU able to perform any of the operations. So, for the proper functioning, the computer requires memory for the storage of data, and some memory is inside the CPU. This is known as a register. As I mentioned before, this is the temporary memory. Register stands for a set of 1-bit storage devices. For example, a 4-bit register would mean 4 bits of data can be stored in this particular register. So, depending upon again the size of the CPU, the size of the data that we are manipulating, the computer capability, the size of the register is accordingly also decided. Now, other bigger storage memory spaces are known as primary memory or the main memory, which is going to have more available locations for storage of the data, and this data can be again stored permanently or it can be stored temporarily based upon the kind of memory, whether it is a volatile memory or it is a non-volatile memory. Now, CPU can work with information available in main memory only. So, whenever there is the temporary memory, as I told you, is a volatile kind of a memory. So, for any work to be done by the CPU, the data has to come to the CPU and then only it can operate that data via the main memory. To access the data from the memory, 2 special registers known as the memory data register and the memory address registers are used. So, data and program is stored in the main memory finally. Now, while executing a program, CPU brings instructions and data from the main memory, performs the task as per the instructions that are fetched from the memory, and after completion of the operation, the CPU stores the result back into the main memory. So, memory is serving as the crux for the entire functionality. The data, whenever it is inputted from an external device, is first brought into the memory, then CPU fetches this data from the memory, works on that, stores it back to the memory, and via this memory the data is outputted. Now, coming to the main memory organization, how the memory is organized. So, main memory unit is the storage unit that has several locations for storing of the information. This can be considered as an array, a 2-dimensional array wherein each block that is found by the intersection of a row and column is able to store some data. Now, size of the memory will depend upon again the size of the data capability of the system under consideration. So, the capacity of the memory module is specified the number of memory locations and the information stored in each memory location. So, a memory module of a capacity say 16x4 includes that there are 16 memory locations in the memory module and each location is capable of storing 4 bits. So, when I mention 16 cross 4, 16 memory locations of 4 bits each. So similarly, higher order of the memories can also be used depending upon the capability of the machine, how flexible the machine is, how advanced the architecture is. Now to indicate or point to a specific memory location, we need to know the address of that particular memory location. So there are two types of operations that are seen while working with a memory. There is a read operation and there is a write operation. Read means to retrieve the data that is there in the memory. That means to read from the memory and bring it to the CPU register, reading from. And the other operation is write operation, which is writing into, wherein we write the data into the memory location from the CPU. So as I mentioned and as was there in the block diagram, there is a two-way communication between the CPU and the memory, whereas for input and output device there is only one-way communication. So the communication between CPU and the memory is whenever reading from the memory or writing into the memory. So now how this operation of reading and writing is carried out? This is carried out with the help of a signal line to differentiate between a read and a write operation. That means how will the CPU know whether the write operation has to be performed or a read operation has to be performed. So this signal line, whenever, for simplicity's sake, we assume that whenever it is carrying a 0, it means a read operation is to be performed, and when it is carrying a 1, a write operation is to be performed. So usually the representation is the most significant bit is represented by this 0 or 1, which indicates a read or a write operation, followed by the address of the memory location where the read operation or the write operation has to be performed. Now to transfer the data from the CPU to the memory module and vice versa, we need some connection. This is done with the help of a data bus. A bus is able to carry the data, and the size of the bus depends upon the size of the data which is being manipulated by a system. So for example, for an 8-bit system, the size of the data bus will be 8-bit long, and this data bus will carry the data from the memory to the CPU during a read operation and from the CPU to the memory during the write operation. Now to specify a particular memory location where we want to store the data or where we want to fetch the data from, we use the memory address. Each location can be specified with the help of a binary address. As I mentioned earlier, the system relies completely on the combinations of zeros and ones, so a binary address is used. If we use 4 signal lines, then we can have 2 raised to power 4, that is 16 different combinations for these 4 lines, provided we use 2 signal values only, that is 0 and 1, as is the case for your binary number system. To distinguish these 16 locations, we need 4 signal lines. These signal lines are used to identify a memory location, and they are called as the address bus. Similar to the data bus, there is an address bus, while a data bus is carrying the data which is input by the user and is to be stored in the memory, or the data which is being retrieved from the memory. The address bus, on the other hand, is carrying that address in the memory from where this data has to be fetched. So both of them are working complementarily. First, the address is identified via the address bus. Then based upon the signal line giving a 0 or a 1, a read or a write operation is to be performed, and based upon which operation is chosen, the data bus either fetches the data or reads the data from the memory, or it delivers to the data to the memory, that is writes the data to the memory. Now the size of the address bus again depends on the memory size. For a memory module of a capacity of 2n locations, we need an n-bit address line, that is the address bus is of the size n. Now an address decoder is generally used. Address decoder is a digital device which is used to decode the address that is present on the address bus. As I said that for example, a 4-bit address bus is going to address a location which is 16-bit long. So this 4 bits being converted into corresponding 16-bit address is what is carried out by this decoder. So for a 16 cross 4 memory, the size of the decoder will be 4 by 16. So the size of the address bus will be 4-bit and the size of data bus will be 4-bit for such a case, and the size of the decoder will be 4 by 16. So there is a control signal which is usually referred by R by W, whereas R stands for read and W stands for write. If this R by W signal is 0, we perform a read operation, and if this R by W is 1, we perform a write operation. Now if the contents of the address bus, let us assume, is 0101 and the contents of data bus is 1100, and RW is equal to 1. So RW is equal to 1 indicates a write operation. Then it means that the data which is carried by the bus, which is 1100, will be written in the memory location which is expressed by 0101, whose digital equivalent is 5. So at location 5, this data will be written because the same has been instructed by the different associated buses and lines carrying the relevant information. So this entire information is decoded and provided to the CPU, and under the influence of this data set, it is going to perform this said operation. So if the another example of a read operation can be if the data bus address bus is containing the address as 1011 and the read write line reads 0, which means the read operation has to be performed, then the contents of the location 1011 will be placed in the data bus. That means the data will be fetched from this particular memory location and placed onto the data bus. Now coming over to the memory instruction. Now we need some more instructions to work with the computer. These instructions are given to the computer whenever there is some internal operation that has to take place inside of the system. So apart from the instruction needed to perform task inside the CPU, we need some more instructions for data transfer from the main memory to the CPU and vice versa. A number of instructions can be provided in computer depending upon the signal lines that are used for providing the instructions, which is basically the size of the storage devices of the computer. For uniformity, generally all the sizes are chosen to be the same. The data bus, the memory address bus, all of them are used to be of the same size. For example, on a 16-bit machine, the total instructions that can be implemented is 216. So first we have to store all the instructions of a program in the main memory, and CPU can work with the contents that are stored in the main memory. And instructions are usually executed one after the other, that is in a sequential manner. Now, as I mentioned earlier, the earlier computers were the initial computer prototypes that were developed were not able to store a program. Now we have come up with the computer systems which have a storage facility, that is they are stored program computers. So they are based upon the model proposed by Van Neumann. So these systems are referred to as Van Neumann based systems. In this concept, the Van Neumann concept states that programs and data are stored in the separate storage units called memories. So central processing unit is the main component of the computer that can work with the information stored in the storage unit only. This concept was proposed by Van Neumann in the year 1946 and his colleagues when they began the design of a stored program computer at the Institute of Advanced Studies in Princeton. That is why this computer is named as an IAS computer, IAS standing for Institute of Advanced Studies. Now, this block diagram here shows the first generation computer, which is the IAS. This has different functional blocks. You can see there is a data processing unit and there is a control unit. So this is essentially the CPU, the bigger block, and on the outside we have IO devices, the input-output devices, and the main memory. There are instructions and data that are carried to and from the input and output devices and the memory to the CPU and back. Now, CPU is divided into two parts, the data processing unit, the main block into which is the arithmetic logic circuit, and the control unit, which has different control circuits and different registers for carrying the information between the data processing unit and to the memory and the IO devices. We will be discussing these one by one as we move forward. Now, the IAS computer has basically three units. Like any other digital computer system, it has a CPU, the main memory, and the IO devices. Now, CPU is the main unit of the computer which is responsible to perform all the operations. Now, CPU of the IAS computer again has a data processing unit and a program control unit. The data processing unit contains high-speed registers for temporary storage of instructions and memory address and the data. The main actions specified by the instructions are performed by the data processing unit with the help of the arithmetic and logic circuits that it has in the data processing unit. The control circuit in the program control unit are responsible for fetching instructions, decoding, Opcodes refers to the operation codes. For example, an AND operation or an addition operation or a subtraction operation, they are specified by codes called as the opcodes. So decoding of the opcodes is also carried out by this control unit. Then controlling the information movement correctly through the system, that is whether it has to go from the memory to the memory, which input device it has to be fetched from, which output device it has to be displayed onto, is all carried out by this control unit, and then providing proper signals for all CPU functionality. Now, the main memory unit of the IAS system is uniquely specified by the memory address of the location. The data transfer between memory unit and CPU takes place with the help of a data register, which is called as DR. When CPU wants to read some information from the memory unit, the information first brings to the data register, and after that it goes to the appropriate position where the manipulation operation has to be performed, that is the memory location where it has to be fetched from or read into. Similarly, data to be stored in the memory must also be put in the data register first, and then it is stored in the appropriate location in the memory unit. So, DR register, the data register, essentially acts as the intermediate transport carrier between the memory and the CPU. Now, the address of the memory location that is used during the memory read and write operation is stored in the memory register called as AR, which stands for the address register. The information fetched from the memory is an operand of an instruction. Now, operand means the data which is to be operated upon. Then it is moved from the DR to the data processing unit. Now, two additional registers for the temporary storage of these operands and results are also there in the data processing unit. These are all referred to as accumulator AC and multiple quotient register MQ. Talking about the different types of microprocessor systems that have been there, the AC or the accumulator plays a very vital role. As I mentioned earlier during my discussion, that accumulator is a temporary register which is going to be storing the temporary result before it is finally reaching its destination, which can be the output device or which can be the memory. So, this is a temporary placeholder which is going to be holding the data while the data is being manipulated in the CPU. So, this accumulator is not part of the main memory, but it is the part of the CPU. Now, IO devices. The IO devices, as I mentioned, they are also called as the peripherals because they are usually connected to the periphery of the CPU. So, input devices are used to put information into the system, and with the help of the input devices, we can store information in the memory so that the CPU can use it. Program or data is read into the main memory using the input devices or the secondary storage under the control of CPU input instructions. Now, as I mentioned earlier that the memory can be a secondary or a primary memory. So, based upon which memory is being addressed, the CPU is either going to fetch from the main memory or it is going to fetch from the secondary memory that has been inserted into the system. The output devices are used to output the information from the CPU. If some results are evaluated by the computer and it is stored in the computer, then with the help of the output devices, we can present it to the user. The output data from the main memory goes to the output device under the control of the CPU, that is the control unit is going to be giving the relevant instructions for the transfer of data from the CPU to the output device. Now, this brings us to the history of the computer architecture, how actually we began and have come over to the kind of systems that we have today. Now, computer architecture has been a very fascinating field of study and which depends upon selecting the kind of interconnecting hardware components to create a computer system that is able to specify the functional performance requirements and the cost goals. Now, commercially used systems are quite different from the personal computers that we are using, and both have been designed based upon the target audience, the target user base, which is going to be working upon these systems. Now, computer architecture will be depending upon the kind of attributes that are required by the programmer, and they have a direct effect on the execution of the program. Now, computer architecture concerns machine organization, interface application, technology, measurement and simulation, which includes the instruction set, the format of the data that is to be manipulated, the principle of operation and the features such as organization of programmable storage, registers used, interrupt mechanism and so on. It is the combination of instruction set architecture, machine organization and the related hardware which brings up the entire architecture of the computer system. Now, moving through the history of the computer development, the first generation computers which came into existence were the era of the decade of 1940s to 1950s, and that was the era of vacuum tubes, wherein the vacuum tubes, which were huge tubes, were used to do the switching operation. So, the first introduced computer was the ENIAC, which came into consideration in the year 1945, and it was designed by the two computer scientists, which were Mauchly and Eckert, and which was built by the US Army during the World War II. It was a huge system using around 18,000 vacuum tubes and 1500 relays that were used to build this ENIAC, and it was programmed by manually selecting the switches and setting the switches in order based upon the kind of operation that required. After the ENIAC came the UNIVAC, which was the first commercial computer introduced in the 1950s. Then John von Neumann, which we just discussed the IES architecture. So, his associate Goldstein and von Neumann took the idea of ENIAC and developed the concept of storing program into the memory. So, the kind of system that they introduced was basic functionality was that of an ENIAC along with the memory facility. So, they introduced the memory concept into the computer system. So, this is commonly very popularly known as the von Neumann architecture, and in fact the system that we use today is also the descendant of the von Neumann architecture only, and it has been the basis of virtually every machine that has been designed since then. The main features being the electron emitting devices it used, the data and program storage facility, using a single read or write operation. As we mentioned, an RW line, a single line is able to decide whether a read or a write operation is to be performed. Memory contents become addressable, wherein we can address a particular memory location regardless of the content that machine is carrying. And the machine language or the assembly language was introduced. That means the language which is understandable by the computer, and sequential execution of the instructions were the highlighting features of this von Neumann architecture. After this came the second generation from the 1950s to the 1964. This period is marked by the revolutionary introduction of the transistor. William Shockley and John Bardeen, their associate Walter Brattain, invented the transistor, which reduced the size of the computer considerably and improved its reliability. The small size transistors completely replaced the vacuum tubes, which reduced the size, made the computer more handy, though still it was much larger than the modern day computer that we were using. But vacuum tubes were completely replaced by the transistor, so the sizes became very small. Second generation is also marked by the first operating system to be introduced, which was able to handle one program at a time. That was the limitation, but operating system was the first concept which was conceived during this period of time. This had on-off switches instead of the manual switches that were used in the first generation computers, and these switches were controlled electronically. They had high-level program languages as contrast to the assembly-level language program which was used in case of the first generation computers, and it also used floating point arithmetic which was first introduced during this generation. Then moving on to the third generation of computers, which was the period from 1964 to the 1974, which marked the introduction of the integrated circuit technology, or the IC that we commonly call. Now, what is an integrated circuit? An integrated circuit is a circuit in which many circuits are embedded onto a single chip. Now, integrated circuit technology has seen a vast improvement over the last few decades, moving on from a fewer tens of registers on an IC to the millions of registers, millions of circuits that are being embedded onto the IC nowadays. So, microprocessor chip came into existence with the third generation of circuits, third generation of computers with the help of this IC. So, microprocessor chips were there which had thousands of transistors, and the entire circuit was there on one computer chip. The memory was the semiconductor memory that was being used. Multiple computer models with different performance characteristics were introduced during this period, and the size of the computer reduced drastically further from the previous two generations. Now, the fourth generation, which can be regarded as the current generation of the computer system, beginning from the 1974 till date, which marks the advent of very large scale integration, that is VLSI, and ultra large scale integration, which is ULSI. Very large scale integration stands for the fact that a large number of millions of transistors can be fitted onto the one single chip. That is how the small size of the transistor has been achieved to date, such that the circuits, thousands and tens of thousands and up to millions of circuits can be embedded onto one single chip. So this combines millions of transistors. There is a single chip processor and the single board computer that emerged during this era. There was this one motherboard, as we all must be aware, which contains this single microprocessor chip along with all circuitry on this one particular board. The creation of a personal computer was a highlight of this era. The computer became small, a personal computer which was able to fit on a tabletop, and a use of data communication also played a very big role during this fourth generation of computer system developing. And massively parallel machines came into existence. By massively parallel machines, we understand the machines which were able to do multitasking, parallelly handle multitudes of tasks, as opposed to the single program systems that were introduced in the first and the second generation of the computer development. Now, with the development of the computer through these four generations, the instruction set has also enhanced drastically. Beginning from the first generation, which saw a very small instruction set and a limited capability of computer, the computer these days are able to handle many complex instructions and able to perform many complicated operations. Now, seeing the evolution of the instruction set architecture, or the ISA abstract interface between the hardware and the lowest level software has undergone a wide variety of evolution over the past few decades, where the 1950s marked the single accumulator EDCAC instruction set. The 1953 had an accumulator plus index registers, which were introduced in the Manchester Mark I, IBM 700 series, and separation of programming model from implementation was introduced in the 1960s, with 1963 introducing the high-level language-based B5000, 1964 wherein the concept of family was introduced by IBM via IBM 360. Then general purpose register machines came into existence in the late 1970s. Between 1977 to 1980, the CISC, complex instruction set computers, were introduced by VAX and Intel 432. The 1963 to 1976 load store architecture was introduced, which was seen in CDC 6600 and Cray 1. Then 1987, the RISC, reduced instruction set computer, came into existence, which were by SPARC, HP and IBM. Now, a typical RISC system, which is currently also very popular, having a reduced instruction set, has a simple and no complex addressing. Constant length of the instruction is there, usually 32-bit fixed format has been there. Large register file is there, hardwired control unit, and no need for microprogramming. So this was a very highly capable instruction set, yet reduced complexity, making it more user-friendly. This is what currently being used. Now, major advances in computer architecture are typical associated with the landmark instruction design set. So, as and when more and more instructions are added, more flexibility is introduced, and more flexible the architecture becomes, and more evolutionary advanced that architecture is considered. So, the main concerns for computer architecture through the last few decades have been from 1930s to 1950s. The main concern was introducing computer arithmetic, microprogramming, pipelining, caching of the memory, and time-shared multiprocessor. 1960s marked the operational system support as a vital concern, especially memory management and introduction of the virtual memory. 1970s to 1980s, the instruction set design specifically for compilers, vector processing and shared memory multiprocessors, and the introduction of RISC, that is the reduced instruction set computers. 1990s marked the design of the CPU, the memory system, the IO system, multiprocessors and networks came into the existence. The 2000s were characterized by the special purpose architectures, functionally reconfigurable. Special consideration was there for low power mobile processing and chip multiprocessors and memory systems. The smartphone that we are using nowadays has a massive computing capability, and that is the result of the special consideration for mobile and low power devices. These devices are capable on working on low power. Plus, as the size of the device is reducing, the requirement of the low power has become a very, very prominent feature in the design of the circuits, and in turn in the design of the microprocessor, followed by the design of the computer architecture. And parallel processing has become a very, very important concern with the computers that are coming in today. The computer should be capable of handling massive amount of data, at the same time being capable of performing multitudes of functions at the same time. Now, under rapidly changing set of forces that have guided the computer technology itself has undergone a dramatic change. The processor clock rate has reduced at about 20%, has increased at about 20% per year. The logic capability has increased at about 30% every year. The memory speed 10% increase every year. Memory capacity by 600 increase every year. Cost per bit improves about 25% a year, and the disk capacity has increased at 60% a year. Moving from the floppy disk, we came on to the DVD drives, and now the Blu-ray discs are there. So, which goes out to show the amount of data storage capacity has increased. And this is again attributed to the computer architecture becoming so diverse, becoming so advanced that the data handling has increased, and hence the data storage has also increased. Now, having seen the history of computer architecture, let's see how the history of computer organization has varied over the last few decades. Now, computer organization, as I mentioned before, is how the features are implemented, how the blocks are interconnected, and how the designer has specified the signals such as control signals, the interfaces and the memory technology, and these remain hidden from the programmer or the user. So, a stored program computer, which is the computer we are using today, has the following basic units: processor, which is the center for manipulation and control; memory, which is for storage; I/O, which is for inputting and outputting; and data path and control, which is for collection of parallel wires, transmitting of data, instructions and the control signal. So, computer organization is going to essentially be the interconnection of all these blocks. So, it is the capabilities and performance characteristics of these principal functional units which identify your computer organization. So, architecture can have a number of organizational implementations, and organization differs between different versions. For example, Intel's x86 family shares the same basic architecture, and the IBM System 3670 family shares their basic architecture. Now, coming over to the evolutionary progress of the computer organization, the 1977 marked the 8080, the first general purpose microprocessor being introduced, which had an 8-bit data path and was used in the first personal computer. 1978 marked the introduction of 8086, which is a much more powerful 16-bit 1 MB addressable processor, which had an instruction cache. That means it could prefetch the instructions ahead of time while a current instruction was executed. Next instructions to follow in the sequence were prefetched. That increased the speed of the 8086 much fast, making it much faster than the previous version, which was 8080 and 8085. 1980 saw 8087 coming into picture, which was a numeric coprocessor. Now, ALU of a system has a limited capability of being able to perform the addition, subtraction, multiplication, division and the logical operations. The numeric capability can be increased by putting this numerical coprocessor in the system, which is not only able to perform these basic operations, it is also capable of performing operations such as exponential calculation, logarithmic calculation, trigonometric functions and so on. Now, in 1982, 80286 comes into picture, which was a 24 megabyte addressable memory space plus more number of instructions. The 1985 saw the 80386, which was a 32-bit. New addressing modes were introduced and it had support for multitasking. Now, 1989 to 1995, a lot of microprocessor chips came into existence, which modified the organization. 80486 which had an inbuilt math coprocessor. Pentiums came into picture, Pentium Pro came into picture, and 1995 to 1997, Pentium 2 was introduced. 1999, the Pentium 3, and 2000s, the Pentium 4, the P4, the highly acclaimed P4 was introduced. In between, the systems like Celeron and also were also introduced. Now, evolution of memory has also gone over the last 3 decades, has gone through a lot of vast changes. The memory speed has increased, the memory capability has increased, a lot of features have been added to the memory, beginning from the basic RAM or the dynamic RAM, which was introduced in the 1970s, to till date we have come up with the enhanced dynamic RAM, which is dynamic or power refreshed RAM, and is also known as the cached RAM or the cache memory, which we commonly refer. Now, buses also, which buses are as I mentioned earlier, there are 2 types of buses. There is a data bus and the address bus. These bus architectures have also undergone a massive change over the last few decades, beginning from the Video Electronic Standard Association bus, VISA bus, which is a 32-bit bus, which relied on the 486 processor to function, to the ISA, that is the industry standard architecture, which was 8-bit or 16-bit with width of 8 to 16 bits, 8.3 megahertz speed, 7.9 or 15.9 bandwidth accordingly. To extended industry standard architecture, PCI, which is peripheral component interconnect, PCI-X, which is up to 133 megahertz bus speed, 64-bit bandwidth, 1 gigabyte per second throughput. To accelerated graphic port, which is currently being very popularly used, which carries 32-bit data, 66 megahertz, 254,3 bandwidth. Now, moving on to the arithmetic and logical unit, as I said that this is a very important part inside of the CPU, and this is where the entire data is being manipulated and processed. So, this is able to perform a lot of arithmetic functions and the logical functions. Now, to identify between these operations, they are grouped under arithmetic and logical, and based upon the 3 control lines that are fixed, it is chosen which of the operations is to be identified. The bits are specified. There are 3 bits, a C2 bit, a C0 and a C1. The C2 bit identifies the arithmetic operation, identifies the group. The C1 identifies the arithmetic operations, and C0 the logical operation. As can be seen from this table, based upon C1 and C0, arithmetic operation for C2 is equal to 0 is performed, and logical operation for C2 is equal to 1 is performed. So, 0, 0 for arithmetic stands for addition, while for logical stands for ORing, 0, 1 for subtraction and ANDing, 1, 0 for multiplication and NOT operation, and 1, 1 for division and XOR operation. So, this is a general block diagram of an ALU. As can be seen, there is a decoder, operation decoder, which is accepting these 3 bits C2, C1, C0. Depending upon the combination, it is selecting one of these operations. A, B and C marks the 3 blocks which are the temporary registers, one of them storing one operand, other storing the other operand, and the third one storing the result. So, as can be seen that an operation C is equal to A into B is to be performed, then A will be carrying one operand, B will be carrying the other operand, and the result will be stored in the register C. So, we should have some hardware implementation for these basic operations, and for the basic operations to be implemented, some complicated operations which are not feasible are implemented directly by the hardware. So, there are several logic gates that are utilized for basically building upon these functions. These logic gates are basic gates being AND gates, AND gate and OR gate and a NOT gate. Then there are these universal gates which are NAND gate and NOR gate, NAND standing for NOT of AND, NOR standing for NOT of OR, and then there are these exclusive gates called as XOR gate and an XNOR gate. As an example, for an AND gate, there is a symbol that specifies an AND gate. The AND gate gives an output high if both the inputs are high. So, as can be seen from the truth table, whenever both inputs are high, that is A and B are 1, 1, then only the output will be 1. For all other combinations, the output remains 0. Similarly, for an OR gate, the output is high whenever either of the input is 1. So, if it is a 0, 1 or a 1, 0 or a 1, 1, then the output will be 1, otherwise it remains a 0. The XOR gate is an exclusive OR gate which gives an output high if either of the inputs is high. So, only in the case of 0 1 or 1 0 will it give me an output 1, else it gives me an output 0. Now, there are various arithmetic circuits that can be implemented using these logic gates. Different equations are derived, which is an altogether different stream of digital electronics that can be independently explored. There are the equations for the implementation of a function that can be derived. These equations can be solved using different techniques of Boolean algebra, techniques such as use of Carnot maps, commonly called as the K-maps, techniques such as the Quinn-McCluskey method to come up with simplified functions. Once these simplified functions have been identified, these functions can be implemented with the help of logic gates, wherein AND, OR and NOT are the basic gates that can be used. And to make the system more flexible, a single kind of gate can be used, which can be a NAND gate called as the universal gate, or a NOR gate, which is again a type of a universal gate, can be used. The common examples of these circuits that are implemented, the digital circuits arithmetic for performing arithmetic operations, are a binary adder, which can be further classified as a half adder or a full adder. A half adder is capable of adding 2 bits of the number together without the consideration of the carry generated from the previous operation, and it gives us 2 outputs, a sum and a carry. A full adder, on the other hand, adds these 2 bits along with the carry generated from the previous operation and gives a result as a new carry and the sum. These can be, the full adder can further be then used to implement a parallel adder, which can be a 4-bit parallel adder, which is adding 4 bits with full adding operational capability at the same time. Similar to the adder, the analogous architecture is that of a subtractor, which is again can be classified as a half subtractor or a full subtractor. Using these subtractor, again a 4-bit parallel subtractor can be implemented. So, many such circuits are there, and using the operations of a adder and a subtractor, the operations like multiplication and division can also be implemented, where multiplication is implemented by successive addition method and subtraction can be used to implement the division operation by successive subtraction method. So, using this technique, various circuits can be used, and these are used to basically implement the arithmetic and logical unit. So, with this we come to the end of this lecture. Thank you so much.
Thank you, ma'am. Dear students, ma'am has explained in details the architecture of the computer systems, and she has talked about the gates in large details. If you still have any queries for ma'am, please do write into us, and you want to catch this lecture again on the YouTube once it is uploaded there. Thank you, ma'am. Thank you, dear viewers, for your time. Thank you.